Good day, everyone. This is John Russo. I want to thank you for joining me here today. I'm encouraged you have joined me despite the scary title of this presentation, to begin a discussion with you about the real challenges of realizing a truly automated agriculture system. We are going to dive technically into the research here in a moment, but to develop our common understanding of the context and my motivations for taking the time with you, please indulge me a bit in imagining the future. Picture yourself standing in a field. I'm making this recording to you from Shizuoka City, Japan. Konnichiwa. The photo on this slide shows a nearby tea field. Overhead you can see the fans used, similar to the grape fields in my native California. Let's walk out into these perfectly manicured crop rows and imagine we are standing in a fully robotic cultivated farm of the future. Robotic cultivators move through the rows, harvesting. Overhead we hear the buzz of drones monitoring, and together with vast arrays of sensors sending data into the cloud. And then we have to stop and ask ourselves, how does it all work? With this in our mind, let's try to articulate the title of the presentation: Methods of Using Cloud Computing Technology for Adaptive Management of Large-Scale Networks in Dynamic, Automated, Field-Configured Robotic Cultivation Equipment. It's a mouthful, and as hard as it is to pronounce, the truth is that the technical reality of the vision is harder still. The inspiration for this research has a simple origin. My own educational and professional background is computer systems. Yet for a time, I turned from this to operate a small farm in California where I grew crops and managed an apiary. After many years, I returned to my own origin in the field of computer systems, researching and developing field robotic systems, exploring different applications for automated systems such as the robotic apiculture units and drones deployment systems in the slide above. Thoughts turned to the communication infrastructure. I spent some time in the early days of Sun Microsystems, and we had a phrase: the network is the computer. How much more so for the truly automated farm? Here lies the interest in the cloud. Much of the research I encountered on the use of IoT in the field were fascinating, yet they assumed a fairly simplified system, mainly for data acquisition, with cloud-based applications that do post-processing and analysis. However, the systems we are imagining here today have two fundamental deviations from much of the work that I found. First, our vision requires active cultivation capability. There are sensor networks for sure, and these need to direct the cultivation robots through the cloud-based policies receiving data from multiple sources. Second, we cannot assume system homogeneity. While the replication of field units are likely to be substantially similar, it is apparent that device deployments are not likely to be uniform or static. Even if they are initially, as time progresses, they will change. So, how will this cloud system respond to this change? In my own research and development, I started with off-the-shelf development tools, but quickly I found they often assumed, just like the research, replication of more or less static devices. And when this was not the case, it required constructing new interfaces for each variant device. The natural result is that the prototypes rapidly became too complicated. There has to be a better way. The Ag Cloud Network needs to respond with self-reflection and dynamic adaptation, such as the way the USB bus works on our PCs. So how is this solved? When you don't have the answer, it is often helpful to focus on the way. Borrowing some inspiration from Japan, where I currently reside, the kanji you see here is michi, which means roadway. But it is also the same kanji used in Bushido, which refers to the samurai moral code, or their way. To understand the evolution of our vision, let's consider the michi that we are on. Here is the basic hardware architecture that begins to repeat in some of these designs. Initially, a design starts with a single purpose, which can be realized as a single microcontroller. There are many capable IoT controllers out there. Each are quite feature-rich. My own experience shows that development prototypes typically start with one controller that manages all of the attached hardware, including the servos, sensors, switches, pump controls, and whatever else you need. In this sense, they reflect the research on IoT that's out there on the internet. Please note MC1 in the diagram. This is where our road begins. In this research, I used the Maker 1010 Arduino board. I happen to have one right here. Take a look. Nice little board and easy to use. However, as the prototype grew more complex, it became clear that some of the features were really optional add-on hardware units, things that would require change based on field assessments. An interesting aside, Jido means automation or self-motion. While this is not the same root as Bushido, we can draw metaphorical inspiration from this similarity. Therefore, our path leads us to the next step in automation, which is to include the attachment of a small microcontroller to manage the bus and communicate the required information to the primary controller to respond reasonably. As the attachments increase, so do these microcontrollers. MC2, MC3, MC4, these are in the diagram above, and it shows this evolution. In my research, I used the tiny Arduino Nano controller. I also happen to have one of those right here too. This is a fairly limited device, and I chose it specifically for that, to ensure that the system design would be able to handle these types of controllers. And then we move upward into the cloud. If a dynamic interface could communicate capability to the primary controller, and then into the cloud as well, the system can accept new or upgraded attachments even if it never anticipated the additional capability. Let's look at our budding microcontroller community. This slide shows the data flow between the primary IoT thing controller, the MC1, and the attachments. Again, for time's sake, I'm not going to discuss this too much. A quick technical note, though, I2C is a master peripheral model, but that just means that the peripheral doesn't speak unless the master speaks first. So this is easily implemented on a peer-level transport, such as the SMQ, as we're going to need later. Within the message framework, I implemented a lightweight protocol for new device identification. You can see in this slide, device identification is one of the key aspects of dynamic adaptation. Initially, the master controller does not know what's attached. The basic handshake involves the master device issuing a CQ request on all available transport addresses. The single byte CQ probes whether or not an active device exists at that address. Since it's entirely likely that no device exists on any given address, the response only signifies existence for the sake of efficiency. However, if existence is determined, the master device can issue an extended CQX request for additional information about the device itself. The device then returns a device ID. There are no specific requirements for this ID per se, but we're going to see later that the information encoded into it can actually be quite important in allowing dynamic adaptation to attachments and devices that have been previously unseen. Okay, so looking a little closer at the firmware, this protocol is built into the class hierarchy shown in this slide. The dynamically adaptive protocol is realized through a wire wrapper that sits on top of the specific device transport. For time's sake, I'll leave it at that, but basically it abstracts the specific transport protocol into an abstract transport, device, and bus, which can then be used with the underlying transport implementation transparently by the applications. Once the device is recognized, the registers can be either individually set or set as a block with the RX commands. To the extent that the registers control device operation, we can control the device via the cloud through these registers. Now on the other side, this is the cloud server. For the cloud server, I used a Raspberry Pi 3B that I happen to have lying around. I chose the real-time logic open source web server and Lua-based SMQ service. Initially, I tried using the Arduino IoT development system, and then I investigated briefly alternative commercial systems. However, the Arduino IoT system immediately began to display significant limitations with regards to the dynamic adaptation that I was after. Therefore, I used the SMQ service with the real-time logic server. And I use this pretty much out of the box. However, the SMQ service does have a Lua interface, which allows for server-based extensions. This can come in quite handy both for the implementation of cloud policies as well as cloud-based directories, which we're going to see could also be very important to dynamic adaptation to different devices. A little JavaScript code was also necessary. This was necessary for two reasons. One, to implement the protocol that we saw earlier on the server side, and then to implement the user interface on top of that protocol that could respond dynamically to the device changes as it received them over the cloud. Now here we can see the message flow in a cloud agent application. Though the underlying transport is SMQ, we see our now familiar CQ and register protocol commands just as down in the depths of the firmware. Under the hood, SMQ is substantially different than a real hardware device interface in that it does not have an inherent address scheme, and in fact there can be unlimited addresses. This is rather challenging to deal with. It was implemented as message domains as well as additional transport data level, which basically included channels. There was another problem that had to be dealt with. That was of device hailing. The cloud agents needed to be able to hail all existing devices, and they needed to do this without starting a data blizzard. So using message domains, I created a hail channel. All of the devices listened on this channel, and when an agent hailed for device identification, they would receive this message and they can establish a connection back to the agent and deliver the messages privately. That was a nifty little trick. So now let's take a quick look at a demonstration of the system in operation. Take a look at the screen here. This is the initial screen of the cloud interface that was developed for this research. We can see by the dialog in the middle that there are currently no devices connected to the cloud. To my left here, I have one of our experimental test configurations. This test configuration has two controllers that are attached by an I2C connection. On the left-hand side, we see the IoT thing controller. This controller has the interface to the internet and does all the communication to the cloud. Next to it, we see a separate controller. This represents an attachment connected again through the I2C interface. Looking back at the screen where it says no devices connected, we're now going to activate the device and see what happens. So look here, we will turn on both of these devices. They will begin operating. As the IoT thing communicates with the cloud will recognize that there's a new device. We see this in the interface. Now a new thing is available under the description. We can click on that thing to see what kind of capabilities it has. This shows an interface into the thing itself. This has a name of the thing. It also shows some device-specific parameters or registers that could be set. These registers are of different types. Beneath that, we see the display device, an LED display device. This display device shows connectivity to the 3 lights that we see on the main IoT device. LED 1, LED 2, and LED 3. 2 is currently on, but we can change that. We can even activate LED 3 and LED 1, and we see the devices responding to the cloud interface. The 4th panel we see here is a device that is not currently recognized by the system. This was configured into the thing device just as a test, but it's telling the cloud that there is an attachment that it doesn't know what it is, but it has 4 data registers. And these data registers are available. These can be changed. So we can change data register 2 to say 56. That is actually getting sent through the cloud and updated on this attachment, although we have no idea what it is. Finally, at the bottom, panel number 5 shows the attachment interface. These are the top 3 lights on the attachment. Now the device is automatically turning on that first light, and we can see that that's getting represented here on the screen. LED 1 turns on. When it turns off, we see a slight delay, but then the switch actually turns off. So through the cloud, we can see what the device is actually doing from the device. For example, if the farmer turned on the sprayer, the cloud would see that, and we would see that the sprayer device actually turned on. Okay. In addition, these are live connections, so we can turn on lights 2 and 3. You see that just happened. We can even, when the sprayer turns on automatically, or turns off, we can turn it back on again. It will go on. However, eventually the sprayer will, or this demonstration device will begin configuring itself once again. Now here's some particular magic. Here we see the whole system operating and the whole pane. But what would happen if the farmer were to disconnect the attachment? We can simulate that here. This wire you see here is actually the clock signal to the I2C connection to the device, the attachment device. We can actually pull that out, which I've just done now. Immediately we see that there's no more updates from the device. The display has stopped changing. It just simply reflects the last known status. Eventually, the cloud notices that the attachment is no longer there, and the interface dynamically reconfigures to show the new true device configuration, which is simply the thing. Suddenly we would notice in the cloud that there's no longer an attachment there. It's just the tractor. And the reverse is true. We can take this clock signal and we can plug it back in. Say put fertilizer distributor on the tractor. We can see that the cloud recognized that and added the device panel back to the configuration, and we're now getting real-time updating of the device. Now that we've seen the system design and an example of it working, let's reflect on some of the lessons that we learned. For the sake of time, I'm not going to discuss all of them. However, I am going to focus on the device IDs used in the CQX responses, since this is so important. The CQX response must include a device ID, as I previously mentioned. However, without uniqueness, the ability to effectively use the device on the cloud is eclipsed. Consider for a moment if all the devices simply returned 0. You would know that there were devices out there. You could even access their registers, but you wouldn't be able to intelligently use them. Now, the next step would be to have random, unique device IDs for each of the devices. This would be a step up. You would know that the devices were distinct, and if you recognized the ID, you would be able to use them intelligently. However, this does not solve the problem for device use of previously unseen devices. If you don't recognize the device ID, then you're not going to be able to use the device intelligently. Therefore, it turns out that encoding device class data into the ID allows for new devices within specific classes to be used and managed to the extent that the device type is known, and this can be done even if the specific device and extended unknown capabilities are not known. And further, if the information is kept in a cloud directory, perhaps implemented in the Lua server, new device IDs can be dynamically registered, even automatically by the device itself. This would be an important capability in a production system that wanted to maximize flexibility in a dynamic device environment. So in summary, we saw the need for dynamic device adaptation, we saw hardware architecture, and we saw software, firmware, and cloud-based protocol that can actually support dynamic device adaptation. We saw an example of a working system. I hope this presentation has provided a useful overview of how cloud technology could be used to harvest data and manage devices in an unpredictable and dynamic automated field environment. As I try to understand where to focus in the future, I would very much appreciate your feedback and discussion. I'm very interested in your thoughts and insights on how you see such technology used in the future. Also, you might have ideas or be aware of certain applications that can use this technology. I'd like to hear from you. Thank you from Japan. Arigato gozaimasu, and please enjoy the conference this week. Bye now.